I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the 2025 FRQs from the AP Physics 2 exam. This is question 3, version J. In this video, we're going to continue our series on the 2025 FRQs from AP Physics 2. This is question 3 from version J. This is the experimental design question. So the experimental design question is laid out where you're going to write a procedure, and then from that procedure, you're going to find an unknown value. So that's part A, so let's talk about how we're going to do that. So in this problem, we are given a resistor that has an unknown value. We also have a capacitor with unknown capacitance, but we have the plates that are exposed so we can measure the plates. We're also given a battery of known electric potential. We have some wires, we have an ammeter, we also have a switch, and we have a ruler as well. So let's talk about a procedure that we're going to take measurements. So in the procedure, you only need to talk about measurements that are taken. It's in the calculations portion, the second part where you talk about what you're going to do with those measurements. So the first thing we're going to do in describing the procedure is we're going to take the ruler and we're going to measure the sides of the plates of the capacitor as well as the separation between the two plates. So we have values we can calculate the capacitance. Then we're going to place all the elements, the wires, battery, resistor, ammeter, capacitor, and switch in series. And we're going to leave the switch open so that no current can flow through immediately. Then what we're going to do is we're going to close the switch and immediately record the current the moment that happens, because at that point there's no charge on the capacitor, so the resistor is getting all of the current going through it. So that means we can use Ohm's law to find a experimental value for the resistor. So then what we're going to do is we're going to open the switch, and then we're going to use a spare wire to place on either side of the parallel plate capacitor to discharge it so the charge can flow from one plate to the other, so there's no excess charge on either plate. And then this is always a point in the FRQ for the experimental design is you have to talk about reducing uncertainty. So what we're going to do is we're going to repeat steps 4 and 5, where we're going to close the switch immediately, record the current, and then open the switch and discharge it. We're going to do this process at least 10 times, so that way we have 10 different measurements of current so that we can have a more accurate value measurement of that current. Part B asks us to describe how the collected data could be used to analyze and determine tau, the time constant. And we want to include references to an appropriate equation or relationships measured and known quantities. So first off, we're going to rearrange the values in Ohm's law to solve for resistance after we average all the values of the currents. So we have one current value that's very accurate with our average measurement for our 10 trials. Now we know the value of the resistor because we have a electric potential value for the battery that is known. So we can use the potential of the battery divided by the value of the average currents that we found to calculate the value of the resistance. Then we can use the measurements on the capacitor to calculate the area of the plates. Then using the area and the separation of the plates, we can calculate the capacitance using the capacitance equation, which is kappa, which is the dielectric constant, which was stated as air, is 1, then multiplied by epsilon naught, which is a constant, and then we multiply by the area and divide by the separation between the plates. Then finally, we have a value for capacitance and we have a value for the resistance. So then we can multiply those two values together, and that's going to give us an experimental value of our time constant, and a very, hopefully very accurate one with the 10 different measurements that we took. So the experimental design question then transitions now to a different question in a different experiment. So now we have the data that's given, and what we're trying to do is we're trying to find the value of a capacitor that has an unknown value. So this is a different parallel plate capacitor, so it switched it up on us. And the values of the absolute value of the change in potential across the capacitor is measured, as well as the charge that's stored on one of the plates. So remember that the Q value in our capacitance equation is just the charge on one of the plates, not the charge on both plates. So we want to indicate quantities that we're going to measure from table 1 or make additional columns to be able to calculate the capacitance. So we can go to our reference table and find the equation that the capacitance is equal to the charge on the positive plate divided by the potential measured across the capacitor. So in this case, we don't have to change anything because this equation is written as a rise over run. So if we make a graph, Q of delta V, that's going to give us a slope that is the value of the capacitor. So that means on the vertical axis, we're going to graph what's given is Q times 10 to the negative 10th coulombs. And then on the horizontal axis, we're going to graph the potential that's measured across the capacitor. Our next question asks us, on the grid provided, we're going to create a graph of the quantities indicated in part C1. So the first part tells us to use table 2 to record the measured or calculated quantities that we're going to plot. Well, we've already have those values because we're not changing anything. So our next step is going to be to clearly label the axes, including units as appropriate. So you also need to make sure that you're going to utilize at least half the value of the graph. So we have to use at least half the graph. So we want to scale this accordingly and make breaks if we need to from 0 to whatever value. In this case, it's spread out enough where we don't have to make a break in the graph, so we can start from 0, 0. But first, what we're going to do is we're going to label our axes, what we're going to graph. So on the vertical axis, we're going to graph charge times 10 to the negative 10 coulombs. On the horizontal axis is the absolute value of the potential measured across the capacitor. Now we need to scale this so we can see that our charge values go from 2.4 to 8, and we've got 30 lines on the left side. So if we did every third one is a value of 1, then that's going to give us 1 through 8 going almost about 2/3, almost 80% away across that graph. And then we go all the way to 10. Again, we have 30 lines, so we're just going to label every third line with 1. Now, the next part is going to be to plot the points. So all we got to do is plot our ordered pairs of 3, 2.4, etc. So we're going to plot our points, and we are going to end up with a graph that looks like this. So we have a straight line graph. So the next part asks us to draw a best fit line for the graph in part C. So here's where you should always use a straight edge. So if you're not provided a ruler on the exam, you're supposed to be provided a ruler. But if you're not, you can always use the edge of your calculator or your Chromebook or your laptop to draw a straight line on your paper. So we draw our straight line and we have our graph recorded for part C. Now, part D wants us to use the best fit line that we drew in part C3 to calculate an experimental value for the capacitance. So we know that the capacitor is just Q divided by delta V, which in this case, the change in Q in the vertical direction over delta V in the horizontal direction is going to give us the capacitance. Now you could do this one of two ways. I chose to do this by picking a couple points on the graph. So we can set the capacitance equal to, and now I've got to pick 2 points that are on my line. I can't pick data points that are not on the line. I have to pick 2 points that fall on the line. So one of my data points falls on the line, that's 10, 8, and another point we're going to use is 5.3 and 4.3. So now we just need to find the slope. So 8 minus 4.3 for my 2 points, but remember, that's times 10 to the negative 10th. So we've got to add that part in. Then we also have on the horizontal, we have 10 minus 5.3, and that's in volts. So then we can evaluate that, and we get a capacitance of 7.87 times 10 to the negative 11th farads is the value of the capacitor. Now I mentioned that there's a couple ways that you can do this. This is one way. Another way that you could do this is you could take your data and plug it into your calculator and do a linear regression. But if you do that, make sure you tell the AP reader that this is what you did. Don't have any magic numbers appear. State that you plugged the values into a table in your calculator, found the linear regression, and your slope value was this, and then explain how you use your slope value to solve for any unknown value, which in this case, the slope was the capacitance. So this is free response question 3 on the 2025 AP Physics 2 exam, version J. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.